So we're going to start today with a continuation of Chapter 11. Chapter 11 was rather long, so we didn't get all of it covered last class. So if there's a few of you who missed last class, go back and review the lecture from last class to catch up on the first half of Chapter 11. I did hear from Angela that it might not have been posted online, which is my fault if it wasn't. Is it up there now? Okay. So it should be up there. If you can't find it, we'll find it tomorrow. So we're going to continue on with steel frame construction, and we're going to move away from the realm of talking about what is a wide flange, how do you measure it, that kind of thing, and we're going to move more into the realm of how do we actually make the building, right? So we talked about the material and the component parts, but how do we actually make the building from that, right? So in the construction process for a steel frame building, and so typically in a building like this, we're talking about at the small scale, maybe Trader Joe's or a Whole Foods or something like that, right? At the larger scale, it could be up to a skyscraper, depending on what we're talking about. But the architect and or the engineer are going to design the building, right? They're going to figure out what this building should look like, and eventually they're going to produce some construction or structural drawings, right? And those structural drawings are going to show the column locations, right? So where are the columns going to go? And this should make some sense, some intuitive sense. As an architect, you would want to know where the columns are going to go. So you're going to decide where they should go. That's your job, right? You're going to define the shapes and sizes of all the members, right? And that's more in the engineer's realm, right? They want to make sure that the beam is big enough to hold the load that they're required to hold and that sort of thing, right? You're obviously going to have to know what loads are going to be on the members. That's, again, in more the engineering realm, right? But you're not going to go any further than that. You're not going to dictate how these various types of connections should be made. You're not going to say there should be 20 bolts in this connection. That's not your job, okay? What you're going to do is you're going to send this job to a fabricator, right? It's a separate independent entity, and their job, basically, is to deliver the steel components to the sites so that they can be built, okay? And so they're going to make up whatever the connections are going to be. They're going to make up the correct lengths of the pieces and that sort of thing. That's their job. Okay? But in order for them to do that, they have to first decide how all of it should actually be made. How many bolts should bolt these two pieces together? What kind of welds should be used? Right? That sort of thing. So the fabricator is going to prepare a detailed set of drawings that will show exactly how and where each piece in the building should go and be used, right? And be connected to another piece, right? They're going to design all the connections that are going to transmit loads. They're going to design how those connections work. Okay? So you as an architect philosophically might say, I want this to be very open, therefore I want you to use moment connections. Right? But you're not going to actually document this is how to make the moment connection. That's the job of the fabricator. Right? So you might advise that's what you're interested in, but it's different than actually designing the connection. The other responsibility of the fabricator, right, is to design the connections in the most economical manner that they can, right? So they want this to be the cheapest end product, right? That meets the basic structural needs, right? The other thing is that these connections, at their discretion, can include a combination of bolting or welding, depending on what they see as most appropriate, right? And so the photograph here is an example of a steel fabricator. They've got a yard outside where they're storing materials temporarily before they can use them. This is more the scrap yard than it is the actual good steel, but you get the idea nonetheless. So the drawings are prepped by and prepared for, or prepared by the fabricator, right? They then send that set of shop drawings, that's what they're called, off to the architect and the engineer for them to review, right? Everybody wants to pass liability to someone else, right? So the fabricator designs all this stuff, but they don't really want to be responsible that the building's going to hold up, so they ship it back to the engineer, so the engineer has to say okay too. Right? So it's kind of double checking to make sure that this is going to work as a building, which is probably good, but it's also to share a bit of the liability because we do live in a litigious culture, right? So these drawings also tell the contractor exactly where and how to install all of the individual components, right? And remember, they're breaking them down into joints, columns, beams, right? And they're all going to have to come to the site, and they're all going to have to be assembled in a certain order so that the building actually appears, right? The interesting thing about this, and we saw a couple examples, photographs last week of, an array of bolts. Let's say that there's 30 to 40 bolts that are bolting two connections together, right? You as the fabricator need to be able to drill all of those holes, right, to be they're only a 16th larger than the diameter of the bolt, right? So you have to be so precise in how you fabricate all those things. So it's not like a fabricator's out there by hand, somebody's out there drilling holes, right? This is a very sophisticated process, high precision required. Certainly much more precision than, say, concrete would need to be, right? So the drawings that they prepare are called shop drawings, which I talked about in the last slide. The engineer is going to review and go through and approve those shop drawings before the fabricator begins fabricating any of the pieces, right? Nobody wants to waste any steel, so they're only going to start construction once it's actually been approved. So a shop drawing might be something as sophisticated as this. This is kind of the complex end of things. It's the 3D model view. Obviously, we can break this apart into all of the individual components. The nice thing with our new BIM systems, our building information management systems, things like Revit, is you can do a lot of this stuff, and the architect and the engineer can all work together to get these things to work, right? Mechanical systems will go in, and we'll have a better understanding of how these buildings come together. Notice we do have our basic column grid that's laid out, so the things that I talked about are still there, right? But we would have details for every one of these individual steel connections, right, and how they would be made. Okay? So we continue on with what the fabricator does. Okay? The pieces, all those individual pieces at the shop, are going to be labeled with codes that indicate where on Earth in this building these pieces belong, right? The nice thing is that we have this new realm of digital fabrication, right? Before, if you were one of these fabricator shops, you had to figure out how to align all these pieces and get those high precision tolerance requirements, right? But now we can set up a computer. That computer can run a CAD/CAM laser or a plasma cutter or something like that, right? That can cut all these pieces out, drill all the holes, cut this precision, which allows us to build far more complex buildings, right? If you've seen like the Frank Gehry Concert Hall in LA or the Guggenheim Museum or something like that, it's a really, really complicated steel building in terms of how it's all coming together, and those types of connections would only be available with this kind of digital fabrication, right? Not something that we can do without that aid. So it's becoming more and more prevalent, right? As many of the connections as possible, right, are going to be done in the shop itself, right? Especially if they involve welds, right? Bolts are relatively easy to do on site, but if you're going to do any welding, you really want to make sure they're done in a shop environment. Why might that be the case? Ideas? Exactly. It's a controlled environment. Controlled temperature, controlled humidity, right? Controlled, basic, is it raining on me, that kind of stuff. So I'm going to go off on a slight tangent. I was at a fabricator shop out on Muir Island probably 7 years ago or so. And they were making, they had done a bunch of the steel that's used on bridges and whatever in buildings and that sort of thing. But at the time I was visiting, they were making hazardous material vessels. So basically like a giant propane tank looking thing, right? Only the size of all of us could be in it, right? Think like railroad car type thing. So they were making these vessels, right? And so they're making it by rolling a certain section of steel into a cylinder and then welding it together, right? And then capping the two ends and welding those together, right? And so what they would do is that as much of this particular vessel that they were making as possible, they would have, right, computer-driven welding equipment actually make the weld, right? Because this needed to be such a high precision weld. But in order to ensure that it met the requirements they need, they actually got out a bunch of ultrasound equipment, very similar to what you would if your wife was pregnant or you were pregnant. They're looking at the baby. They used the same type of equipment to ultrasound the weld to make sure that it was of a quality and of a precision that was good enough for this particular type of high precision manufacturing, right? So the amount of care that goes into how one of these welds is happening just in a shop environment is huge. Now imagine you were one of the welders that was going to do work on the new Bay Bridge span, right? So not only do you not have control of temperature, you don't have control of wind, right? You've got tons of fog rolling in, right? But you're also strapped into a harness hanging, right, hundreds of feet above the bay, and you're trying to do these welds, right? It's not the ideal place to do a weld. So it should be relatively intuitive to say as many of the welds as possible are going to be done in the shop, right? And so that's kind of that's the point of going off on one of these sidebar tangent stories, is to emphasize how important it is to do as much of the welding as possible not on the site, okay? The pieces are then going to be transported to the site, hopefully in the order that they would be used, right? It doesn't do any good to make the topmost beam first, right, and ship that to the site and have it sitting on the site waiting, right? So they're going to start at the bottom and work their way up. So each shipment that comes to the site should be the next realm of steel that's going to go into the particular building. Right? So we move from the fabricator and the world of the fabricator into what is called the erector. Right? And the erector is responsible for actually assembling the steel components on the building site. Right? They assemble all the individual pieces that the fabricator sends. They're kind of this gateway into making an actual building. Right? The erector's workers are typically called the iron workers. Right? You will see stamped on the steel in one of these buildings, if you ever see a building, they will have the union number. The iron workers union will be on all the steel pieces, right? Because they want to advertise that. But it's very specific, and that's their job. It's their job to make this particular building. Right? So, for a multi-story building, right, and we're kind of, a single-story building is rather simple in its construction. So we're going to start with a multi-story building, right? In a multi-story building, the erection is first going to happen, right, for the bottom two stories, right? So we're not just doing one floor at a time. We're going to actually span 2 floors at once, right? And in this particular case, we're actually going to span 3 stories, right? So it can vary a little bit, but that's dependent on the access and can you get these pieces to the site? Are they too long, right? That sort of thing, okay? So what's going to happen is this piece is going to be delivered to the site, right? In this case, it's a column, right? It's coming in numbered with a correct placement for where it's going to go. Then a crane operator is going to come and pick up one end of it and lift the column over the foundation, right? Recognize that the foundation would have already been poured, and it's going to go right over those anchor bolts, right? Those little bolts that come up through the foundation that are going to tie this column into place. Now, recognize the precision requirements for steel, right? Within a 1/16 of an inch, you've got to fit, right? Versus the tolerance requirements in concrete. Okay? Typically on a residential construction job in concrete, the tolerance requirements for where you place an anchor bolt for tying a mud sill into a foundation, plus or minus 2 inches. Right? Pretty generous. On a steel building, we're got to be within a 1/16 of an inch for this to work. Right? So it's much, much more precise on this job. Hopefully the contractors did their job and it does line up where it's supposed to. Right? So the crane lifts this column up, and it puts it down over the foundation, right? And they can fasten it to the foundation loosely. Okay, it's not going to be a permanent installation yet because we haven't plumbed it or leveled it yet, right? I do want to point out a couple things on this image because it's a particularly good image to talk about the fabricator shop and the fact that they're doing as many of the connections as possible ahead of time, right? So this is a column, right? This would be the first floor. This would be the second floor. This would be the third floor. And this joint is going to occur somewhere around waist height. Right, in between floors. But look at each one of these floors at the complexity of what's already been assembled on this particular column. Right? So they're not bringing just the column to the site and just the beam. Right? All of these are special plate connections, right, that are welded and they're going to eventually have diagonal braces attached to them, etc. Right? But all of this welding and this intricacy is done at the fabricator, right, and comes to the site already assembled like this. So you don't have to do this on site. That's the important thing. Maybe. You can go forward. Okay, so that column needs to come down and rest on something, right? And it's, like I said, it's kind of unlikely that the concrete contractors are going to be as precise as we really want them to be. So what can we do to make this a little bit easier, right? What we can use are what are called steel base plates, and they're designed to distribute the concentrated steel load, right, out and then ultimately to a concrete footing. Right? So we're going from the steel column into a base plate into the concrete footing as we go down. And they're going to vary a bit. Right? We can go on the smaller scale into what's called leveling plates. Right? A leveling plate is a thin steel plate, right, that's set perfectly level at the proper height on a bed of grout atop each concrete foundation. So the leveling plate that we're talking about, right, is right here. You guys see that? Right? This is out of the book. This is the column. This is the base of the column above. The leveling plate is this little thin piece that's underneath. Okay? That little thin piece is set at its correct height. Sometimes it has shims underneath, right? Or bolts in here that are holding it in the correct height. It's set perfectly level, and then we're putting grout in underneath it so that it has bearing capacity. Okay? On top of that, we're then lowering this column, right, that has a base on it, and bolting the two together. Does that make sense? But it's at the very thin level, or the thin scale. Okay? If we have a larger steel column, right, where the leveling plate just isn't quite good enough, right, we can eliminate it altogether, and instead, when we put the column down, right, over the anchor bolts that are coming up through, we can put a series of steel shims or nuts underneath that will help us to level and plumb this, right? You guys see the inherent challenge in this, right? We have a small 1-foot square piece and a column that's, say, 40 feet tall, right? If it's off just a fraction of an inch at the base, right, by the time we get up 40 feet, it's off 6 inches or a foot, right? It's leaning in one direction or the other. So you have to be very careful with how you get this perfectly plumb, right? And there's more to the strategy of these stay a little bit loose until you get the rest of the building up, and then you work the whole building as a whole instead of just the individual column. Yeah, Jonathan. This is the concrete footing here, right? This is the grout because this nut or this steel shim that's inserted has to be flexible until you get the whole building plumb. Right. Yeah. No, it's okay. It's okay. It's much bigger scale, right? So this grout just covers up that. Just like with the prefabricated concrete, right? It's always grouted. The joints are always grouted. Same thing happens here. Depends on the size of the column. So the bigger the building, the bigger the columns, right? So the bigger the columns are going to be, and we're going to go one up from this, even bigger, right? So we're going from the small scale. So let's say you were building maybe a Trader Joe's or something that was 1 story, 2 story, something like that. You'd use the leveling plate, right? If you were building a multi-story, say 4, 5, 6 stories, something like that, you'd probably use something along these lines. And again, it's always going to be determined by an engineer. The engineer is going to specify what they think, followed by the fabricator what they think, right? It's going to be in their realm. That's why they go to school. But if we get up into the much, much larger building, right? Think skyscraper-sized building, right? We might separate them out altogether, right? So in this particular case, right, this base plate is shipped independent of the column itself, right? The base plate is then installed and leveled, right? There's our little grout, if I'm reading it correctly, right? Of course, the thing is off the side of the page, so I can't double-check myself here, right? Footing, grout. This is the big base plate that's put in place, right? The column comes down. This little angle bracket holds it in place temporarily until we get it nice and plumb. After that, we go through and weld this to the base plate, right, making it the monolithic whole. So this is the very large scale, right, big, giant columns, right? So you got a little bit more flexibility in this for the really heavy stuff. Yes? Probably getting a little specific would be my guess. Yeah, knowing the concept that you need some kind of a base plate to be able to attach it. Yes. Yeah. Yes, there's obviously a set of shop drawings, but if the concrete contractor wants to make them as precise as they should be, then there has to be some kind of a template. And my guess is the fabricator would probably provide that template to make sure that it matched up, right? It would depend on what the engineer designed in terms of tying that in, because obviously you need to tie the steel column into the foundation and into the rebar of the foundation. So depending on how the engineer designed it, those bolts should be tied into the rest of the rebar system. And so it could come to a plate that's then welded to the rebar. It could somehow be tied in differently, but that's more of an engineering question. Beyond my realm, most of my construction experience is at the residential scale, not at this scale. So I don't have personal experience for what that looks like in the foundation. So after we've got the first set of columns, right, we'll go ahead and put the beams and the girders in place, right? So in this particular image here, we have our first set of columns that have gone up, right? Then we put our beams and our girders in place, right? Girders obviously being larger, beams smaller, joists smallest, right? It's always the same, no matter what we're doing. Most of steel construction, we're only going to be talking girders and beams, right? But joists, as long as you remember the order, right, it's consistent, right? once we have all of these pieces in place, right, we'll bolt them temporarily, and then we can adjust the building as a whole to get it plumb and level. Right? So instead of trying to adjust each individual column separately, we'll bolt the whole thing together, and then we can put cables in that will adjust it and kind of rack it from one direction to the other to get it nice and level. Right? So they're bolted first and then welded as necessary. So the raising gang, right, working with a crane, is going to position each one of these components, and they're going to insert enough bolts to temporarily hold it in place. Right? Only enough to temporarily hold it in place. Right? After they do the leveling and the plumbing, right, not the plumbing like waste plumbing, but plumbing up, right, a gang of bolters is going to follow them and put the rest of the bolts in and tighten them to the required tightness, right? So you can start to see how challenging this starts to get, right? When we have these giant pieces, there's all the bolts that are going to have to connect to this plate, right, coming together. So a lot of times they'll use it's like a long cone-shaped piece of steel to help when the crane's coming in. They'll stick it through each of these holes and try to wedge it to keep them roughly together until they can get one of the bolts through. Right? So they're not going to take one of the bolts and risk ruining the threads on the bolts trying to jam it through. They'll use something to kind of hold it in place until they can get the bolts in place. Right? So after it's plumb, the base plates are grouted. Right? In the large-scale building, the column is welded to the base plate. Right? Everything's tightened up, right? That's completed. Permanently attached diagonal braces are then added, right? If we have any diagonal braces, those are going to be put in, right? Then we move up in the whole building, right? The columns are always made to join roughly at about waist high, right? So if we're spanning 2 stories, it's really the column is 2.5 stories, right? Because we need to get it above waist height. And the reason that we do that, right, is for easy. It's obviously easier to work with, right? But the other factor in that is it never interferes with one of the floor joints, right? If we think about having a joint of a column occurring right here, right, you have the floor coming in, and it's one more piece that you're trying to work through. If you have the column continuous, it's much easier to make this joint, right? So there aren't those conflictions. Once we have that first 2-story piece or 3-story piece, right, we'll move on and move up the building, right? Generally speaking, there's going to be a floor, right? It could be temporary, it could be a permanent floor, and we'll talk about permanent floors down the road, is going to be added every 2 floors, right? And this is for economies. Obviously, if it's a permanent floor, you could do it every floor, but if it's not a permanent floor, if it's just a temporary floor, you don't want to do it every floor because it's twice as much work, right? But the idea here is that if we're way up on a skyscraper, right, there's a limited distance that you can fall before you get to a floor, right? Or better yet, if it's not you falling, maybe it's just your hammer, right, or one of your tools. It's only falling that two floors, right, which is a lot better than falling 50 stories, right? So they give us a nice work surface. They give us some safety, right? So this is kind of classic, right? We've got the ironworkers here, and they can pretty much scale any of this stuff, and it's pretty impressive to watch them, right? But they're working up and down here. Obviously, either the ground or the floor is way down here, and they're just climbing up with no safety harnesses working the building, right? If you were on a much larger building today, you'd probably have to have safety harnesses on, but such is life. So we look up a little bit higher at the steel frame, right? We're working our way up. So these would have been installed, right, in multiple floors, most likely, right? We're getting to a roof section here. We've got 2 cranes working, getting those pieces into place, right? And so we look at it at a much smaller scale building, okay? Similar, we can see a lot of the details that I've just talked about, right? Each one of these pieces is labeled. It has a center point, so we know where that is, right? All of these are prefabricated, and they're bolted into place. Not all of these have every bolt in. Here's a good example. There's one bolt holding this here. We don't have the rest of the bolts inserted yet because we're still working through these particular pieces, right? Oh, here's another good example, right? That's a come-along. This is like a type of winch, right? It's attached diagonally from here across, trying to adjust this particular piece and get the building square the way you want it to. Does that make sense? Right? So the other thing about it is if you're using a crane and you have all these repeat elements that you're going to use over and over again, right, it's a whole lot more time to pick up one piece, put it into place, go back and pick up the second one, put it into place. Right? So what they'll do is they'll chain these together. So the crane will take 4, 5, 6 of these beams, joists, girders, right? Chain them together, and then one time they'll lift from the yard, right, up onto this section of floor, and they'll use the first one, lower down, use the second one. So you can see there's an efficiency to it, right? Typically on a steel building, even a large-scale steel building, say, you guys know the AAA building that's right on 680, right? It's pretty close. That's a steel frame building. 2 or 3 years ago, they were going through this. It was great during this class because I could be like, on your drive home, look at this, right? That size of a building, so 4, 5, 6 stories, the actual frame of the building could go up as quickly as 3 days, right? It's really fast. If the fabricator did their job, right, and all the pieces are assembled correctly, it can go together really, really quickly. And that's a big advantage for a building like this, right, because you can pre-plan a lot of stuff. The other thing that I will point out, we're going to talk about decking in a little bit. Notice that the decking's here waiting to go up there. There's also a stack, and they put the decking on the first floor. So I'm just pointing it out because we're going that direction. Right, so a little bit of a close-up so you can see how these people are working, hanging on here, waiting for that piece to come in. Right? Again, steel's really heavy. Jonathan, what? That's okay. It's depending on the speed of the building, right? How quickly you're building these together. Generally, it's non-permanent because the erection of the building is much, much quicker than the process of being able to pour a concrete deck. So if you're going to use a composite deck, which we'll talk about in just a second, which has steel and then a concrete topping layer on it, you've got to wait for the concrete to cure before you can really walk on it, right? So you've got that delay in the process. Where if they can build a 6-story building in 3-4 days, you don't want to wait for that concrete to cure for 28 days before you can move on and keep building. So typically it's going to be faster. There are other types of decking, like cellular decking, that doesn't involve the concrete topping. So if you were using something like that, it would probably be more efficient to use the actual decking. Does that make sense? So if the decking takes too long, that's when you're going to use temporary decking instead. So we look up, right, at a bigger building here. Obviously, we're working our way up in floors, but we have a temporary work surface that we're working off of, right? Because we can tell by the cityscape that we're already pretty far up in the realm here. The other thing about a multi-story building is once you get up a certain level, right, somebody else can be coming in and doing a concrete topping down below, right? And in this case, I'm guessing that it's actual. It's going to be. Well, it might not be. It looks like it would be a composite decking instead of a cellular decking, but I'm not entirely sure. Right? But you can see there's our joints halfway up a floor, right? And so they're working their way up, right? We've got a floor that's coming in. I think this is going to stay open as like an atrium or something. I don't know the building, but it's a good example. So the other thing that these buildings always have is they have what's called a topping out ceremony, which is this really goofy thing that is like tradition that they have to do. And so the topmost beam of a building, when it gets raised up there, will always have an American flag on one end and a tree on the other end. And I couldn't tell you why, but that's part of tradition, so it happens. It's called the topping out ceremony. It's for that last beam when you finally make it there. So you guys know that I can't lecture without showing some goofy example, right? So we have to show something of a steel building that's a bit unconventional, right? So this is the Prada store in Tokyo, Japan. And this is an entirely steel building, right? But it's a very unconventional steel building in terms of how it's built. So we talked last lecture, right, about the fact that you could have a braced frame that was on the exterior, right, or we could have a core that was providing the seismic stability of a building. So in this case, that frame is on the exterior of the building, right? And it's this lattice, right, of steel members, okay? So it's denser than we would typically see, right? Usually we'd have longer diagonals. But this density is affording something that's different, okay? So each one of these little diamond-shaped pieces, right, is providing a structural stability for the building, but it also provides the hole for where the window goes, okay? And so each one of these is a separate glass bubble, right? The glass pieces themselves were made in Italy specifically for this building, specifically sized for this building. They're not something that is made every day. I think there's 7 different pieces of glass. When the company in Italy made them, they made a certain number of extra pieces. It's like 1 or 2 extra of each type of piece, right? So you better hope that these don't break, because you only have a certain limited number that can be used down the road. So this is a bit of a structural example, but this is also showing which types of glass are being used where on a particular piece of the facade. And we'll look a little bit closer at the entry. So everything in this building works around these steel pieces, right? And obviously there's some extra pieces added to it. We can see from the outside here that some of the pieces pop out, some of them go in, etc. There we are looking at it here. Different view. But, sometimes it's fun to show a slightly different example. Right? Notice the inside of the steel pieces are encased so you don't see the steel anymore. Right? We'll talk about the importance of fireproofing down the road. Okay, so we move on. But we had to show a fun example. Right? So, we need a way of forming, right, a decking material. And by decking, it's kind of like your deck on your house, right? It's some kind of a floor, right, that spans. And so when we're working in steel, we need some way of providing decking that can work with the system, right? So you could build a wood floor on top of the steel, but it kind of doesn't work. They're slightly different building materials, right? And the connections are significantly harder. So instead, we use something that's called corrugated metal decking, right? And what it is it's a thin sheet of steel, and I have only one example in this room that I could find. I swear we had more. I will pass this around. Be careful because the edges are sharp, right? And I don't want you to cut yourselves. But this is an example of that corrugated steel decking, right? This one's actually relatively thick, okay, from a gauge of steel. But what this is it starts out as a flat sheet, right? And then when we add these little corrugations, right, in this example or up here, right, and I'll go ahead and pass this around. I don't need this right now. I can point to the pictures. Don't cut yourself, right? The spanning capability of this particular piece, right, spanning from one beam to another beam, right, is going to be determined, right, by the thickness of the steel, so the gauge of the steel itself, but also the depth of the corrugations. So in that particular example, the depth of the corrugations isn't very big at all, okay? But we might increase the depth of the corrugations to give ourselves a bit more spanning capability. Okay? If we're going to weld these pieces, right, to the steel beams, something like that. Can I borrow that back for just a second? Then you can continue with it, right? So if we're going to take something like this, by the way, this is incredibly flexible in this direction, right? But we don't have a long enough piece. It's extremely stiff in this direction, right? So that's the spanning direction because of the corrugations. So if this were to come in, right, and rest upon, it would probably be resting this way, would be my guess, right, and rest upon a steel beam like this, we would need a way of attaching these two together, right? Remember back to the welding section last week where we talked about the one other type of weld that was called puddle welding, right? This is where it's frequently used. And so the idea here is that you can put the decking down and it supports itself on this beam, right? Obviously this beam would be continuous, but then we can weld through this corrugated metal into the beam, right, with a puddle of weld, and it will actually hold the two together, right? So that's puddle welding, and that's how we attach those together. So we're going to talk about composite decking in a second, but before we get to composite decking, we'll talk about cellular decking, right? And so this concept is we're just using steel by itself, right? So we take a corrugation like that, right? And on top of that, we weld on another sheet, right? That's just a sheet good that gives us basically a cellular piece of deck. And cellular means that there's a cavity in it, but then we have a flat sheet on top of it that we can walk on, right? Or that supports our floor, right? And it ends up looking something like this, right? In this case, there's more gaps than there have to be, right? It's going to vary a little bit depending on the manufacturer of this particular type of corrugation. The space or the cavities inside that corrugated decking can provide great raceways for your electrical wiring, your Ethernet cables, your phone systems, etc. Right? There's a really good example of cellular decking that's used out in the San Ramon area. There's an AT&T building out there that was built a long time ago. I think 70s. I don't know the exact date, but they built it on a system like this, right? Specifically so that when they reconfigured the space inside the building, they could run new wires and adjust where the wires went because they had all these raceways to be able to pull the wires, right? So it ends up being an advantage if you're trying to work with the space and reuse it and change how it's used, right? So that's certainly a positive, right? The most common type of decking, however, is a structural composite decking, right? It's designed to work with concrete and steel together, right, to make a stiff, lightweight topping that you can then walk on, right? This is by far the most common. Best example that's really close that you've probably all been to would be the Target store, right, in Walnut Creek, that moves, that shakes, right? But that's a good example of a composite decking. Basically, what happens is, right, we remember back to the concrete section. Concrete is incredibly good in compression, right? So, theoretically, if we had something at the bottom that was steel and something that at the top that was in concrete, that would be a very efficient way of spanning, right? So this is exactly what we're doing. We're putting the steel at the bottom by making the corrugations, right? And we're putting concrete at the top to deal with the compression. So if I'm standing on one of those floors and it's flexing down, the top is in compression, that's the concrete part. The bottom's in tension, it's wanting to stretch, that's the steel part, right? So it works out really well. The other factor that we already talked about in the concrete section is that steel and concrete have the same coefficient of thermal expansion. So if it gets warm, they expand at the same rate. If it gets cold, they contract at the same rate, which means that they can stay bonded together, which is really the important part of this, right? The other great part about using something like this is the steel decking, that corrugated piece of steel, is basically the formwork for your floor. So you don't have to install any formwork to be able to pour this concrete topping, right? It's already there for you. So it ends up being a very efficient way of making a floor, right? I think I'll come back to this photograph in just a second because I want to talk through the drawing first, okay? So in this particular instance, we have our steel beam. It would be worth your time to draw this. I'll give you some time to draw it, but I'm going to talk through it before you draw it, okay? So, and it's actually, this line should be further back if we're talking about the technical, there's an error in the drawing, but whatever, right? We have our steel decking that occurs here, right? On top of that steel decking, which is resting on the wide flange, the beam, right, is the concrete topping. Usually it's about 2 inches higher than whatever the decking would be, right, but that's going to vary slightly. The other thing that we have, right, are these what are called shear studs, which looks like a giant nail, right? And I think I have an example. I'll dig through that cabinet and see if I can find one in a little bit. But it's welded through, right, the steel decking into the beam below. And this nail gets wrapped around with concrete and helps tie the whole thing together and hold the whole thing together, right? So it's kind of a specialty thing. So I'll give you time to draw it for a second, and then we'll move on. Right? Remember, I'm never going to grade you on the quality of drawings. Just make your scribbles. It's not a big deal. But the act of drawing it will significantly help you remember it. While you guys are drawing, I'll see if I can find one in here. There we go. So while you guys are finishing up with your drawings, I did find a couple shear studs. One's been welded off and one is new. But like I said, they look like basically giant nails, right? And the idea here, right, is that we'd have our metal decking, right, that's coming in and spanning like this, right? We want to be able to tie the whole system together. So we'll put the shear stud and weld it through. There's actually a whole machine that does this, right? And it welds through the decking into the beam itself. And this then provides a nice tie point for the concrete topping to tie this whole thing together. This one's obviously a bit tall because it's sticking up a lot taller than what it would be because we'd want adequate cover in this particular decking. So that would be too much concrete in this particular example, but you get the idea, right, of the shear stud and how it works. Right, so if we jump back a slide, oops, that would be forward a slide. If we jump back a slide, right, and we're looking right here, right, this guy is installing those shear studs. So there's one of the shear studs. He's going to put another one in right next to it, right, and there's a variety of lines for where he's going to put those studs. There's also a whole row of studs here. There's a whole row that goes back there, right? So this is roughly tying in with wherever the beams are that are underneath. Right, and that's going to tie that whole topping layer together. So let's go forward. Right, here's an example. We've got our temporary decking. Actually, this slide should have been back a ways before we got to the other decking. Right, these are just planks getting ready for the steel decking. They would then put the steel. They take these out, put the steel decking in. Right. So on the left here, we've got our temporary planks. On the right, we've got the steel decking in place. Notice that there are a bunch of these little ribs that are included in the steel decking, right? There's a few, if you feel these carefully, the ribs exist. I don't know whether you notice those. Maybe if I can turn it in the right light, you can kind of see those depressions, right? Those ribs and depressions, right, allow the concrete to more carefully bond together, right, with the decking itself. So they tie together. It's like the ribs in rebar. Right, same concept. We're trying to tie those together. Obviously, this guy is welding one of those shear studs into place. Right, there's our row of the shear studs coming across. Right, he's going to continue down this direction to tie that whole thing together. This is unrelated, but there's our two-story column. Right, joint at mid-height. Same thing at the top. Right, connections already welded together at the fabricator. So, just like when we pour concrete on a building, right, that is a concrete building, if we're pouring concrete on a steel building to make this topping, we go through basically all the same steps that we talked about, right? So this is a good review for us anyway. But if we look down here at the area that hasn't been covered with concrete yet, right, we have our corrugated decking, we have our row of shear studs that are in place, okay? So that's good. The other thing is they put a layer of reinforcing, right, that welded wire reinforcing, the WWR, right, inside this, and they're treating it just like a slab would be if it was a slab on grade, right, or a slab up higher in a building. It's the same concept, right? They've got a screed board, so they fill in the concrete. They're using the screed board to get it level, right? After that, do you guys remember what they do? They float it with a bull float, and they actually float it again after they floated it once, right? Followed by a trowel, and then depending on what type of building floor you're going to ultimately put on, you might put a brush pattern on it so it has a little bit of texture to be able to bond whatever you're trying to do as your ultimate floor. You might want it perfectly smooth. It's going to vary, right, depending on what the finish of the building is going to be. But this is an example. Obviously, this is a little bit more complicated than if you were, doing a slab on grade, but it's the same concept, right? So, one of the other problems with steel, right, is that we've got issues with building fires, right, and steel, okay? So if we had a fire in a building, right, this is not a good example even though this building has a lot of steel in it because it has too much wood in it, so we'll skip that. But let's say that there's a fire in a multi-story steel building, right, an apartment building or something, right, or a retail store or, I don't know, something like that. The fire in the building isn't going to be hot enough to melt the steel down into its liquid form, okay? But the problem with fire and the problem with heat in steel is that when you apply the heat, the strength of the steel significantly decreases, right? So it gets weaker, which is the big problem, right? And so that can cause the building to fail. So it's not that the building, all the fire is so hot it's going to melt the steel and the steel goes away. It's that it weakens the steel, right? Often the steel needs to be protected, right, from the fire long enough to get the people either out of the building or to put the fire out itself, right? So we're going to go off on a slight tangent because there's a very good example of this that some of you might even know the direction I'm going with this. But exactly, we're going the direction of the Twin Towers, right? So in this particular example, we had a lot of different things that went into why these particular buildings failed. Okay. Number one, the interesting thing, and what most people assume, is that the impact of the planes into the towers were a significant cause of the structural failure. That had nothing to do with it. Actually, when they designed the buildings in the first place, they designed them to survive the impacts of airplanes, right? So that was built into the structural integrity of the building was perfectly fine. What they didn't take into account was the fact that the jet fuel, right, is a combustible material that's significantly more in quantity and in heat generating capabilities than would typically be in a building of that size, right? So when you have that burning jet fuel, it's a much hotter fire than you're expecting it to be, right? So that's one problem. Number two, the building was all the steel. It was actually steel trusses that were supporting the building. It was fireproofed in a manner very similar to this, designed to withstand building fires, right, which it should be. The problem was, with the impact, a lot of that got knocked off, right, because it's just clinging onto it. It's not something that's permanently attached to it. It's a spray-on material, right? So we lose a little bit of it. Doesn't mean all of it was gone, right? But it was just enough for these trusses, and recognize because it was trusses, the members themselves are smaller, right? And because those members are slightly smaller, it takes less heat to heat them up to the point where they start to weaken, right? So go up to the floor, and I forget what floor it was that got hit. Go up to that floor, right? The combination of the jet fuel, right? The combination of a little bit of this fireproofing being knocked off, right? Caused some of those trusses to start to fail, right? And it was a progressive fail. So we'd have one little cord in that truss fail, right? Which would put more weight on either side, the trusses to either side. Both of those would then fail, right? More weight, and we've got the building that's up higher than those, pushing down on these particular trusses. So you get that progressive failure, right, due to the overheating, right, due to the weakening of the steel, and before you know it, the whole building collapses, right? But it's a really good example of how a combination of factors that you as a building designer, right, couldn't deal with, right? And there's obviously other issues with the fact that the people weren't able to get out because the stairways were destroyed, and there's far other issues that go into this. So I'm not pretending to go off on the lecture, but I think it's a good illustration of the importance of fireproofing and how even if you do fire-proof the building, and even if you do the design the building so that it structurally can withstand the impact of an airplane, those things might not be enough. Yeah. It would depend, and I don't know what the fireproofing was made of in that particular building. My guess is that it was old enough to probably have asbestos in it, which probably is a good thing from a fire rating standpoint, as bad as it is from a breathing standpoint. So I don't know what the rating was on that particular piece. The ratings are going to vary depending on the type and the technology of the material and how they work together. So you'd have to go to the specific manufacturer and see what that material would be rated as. So yeah, we're going to get to some slides, and I think I have the data for the general data for it. If I don't have it in the slides, we can look it up and see the general data. Okay? And if I don't have it in the slides, I apologize. I should have it in there. Right? So if we get to the earliest form of fireproofing, right? The earliest form of fireproofing came in the form of brick masonry. Remember, we talked about brick as being the true fireproof building material because it's a product of fire, right? Therefore, it's a fireproof building material, right? The other thing that we could do is we could pour concrete around one of these. We could build concrete blocks, the concrete masonry units around them, right? But we're trying to use those to protect the steel itself from fire. The problem with this as a strategy, while it works and it actually can look very decorative, right? It's really, really heavy, right? So we're increasing a lot of weight in the building without really getting much for it, right? It's not providing structural value. It's just providing fireproofing value. So it's not the most economical way because you have to increase the amount of structure that's in the building, to actually fireproof a particular piece, right? So we moved from covering it with brick, covering it with concrete, to a much lighter weight solution, which was lath and plaster, right? Which is very uncommon today, right? But it's kind of the precursor to sheetrock, basically. And it's the reason it's effective, and this is true also for sheetrock, which is gypsum board. And I'm gonna every time when we get to interior finishes, I'm gonna call it sheetrock the whole time. It's like people that call tissue Kleenex, like it's in my head. I'm gonna call it sheetrock. It's the brand name. I apologize. It's gypsum board, but if you go anywhere, it's sheetrock, right? It's because that's the brand name. The reason that this stuff is effective, whether it's lath and plaster or whether it's sheetrock, is it takes a huge amount of heat to pull enough of the water out for this to combust, right? Because the structure of the sheetrock or the structure of the lath and plaster has water that's embedded within the structure of the material itself. And in order for that to evaporate, right, or dehydrate, we have to heat it up for a really long time to get it out, right? Which is part of why it works really nicely and why we use it all the time. Right? So today we're not going to use lath and plaster. We're instead going to wrap these columns in several layers of sheetrock. And the reason that it's several layers of sheetrock is not because the large face of the sheetrock is bad. It's that we can leak through the joints in the corners. Right? Anybody a sheetrock taper, and right, a few people know, right, sheetrock realm. Right? You cover all of the corners with tape and mud, but that's not the same as the sheetrock itself. Right? So in this particular instance, we put multiple layers together where they would overlap one direction and then overlap the opposite direction to try to give us better fireproofing at the corners. Right? Obviously, if we did fireproofing on, say, the Twin Towers using sheetrock, same thing would have happened. Right? So it's not necessarily something that can always work. Right? We can also put on what are called spray-applied fire-resistant materials. And clearly, I'm not putting the hour how long they can rate. So I'll look that up and make sure we get that information to you. The spray-applied fire-resistant materials are the most prevalent type today, right? They are not of finished quality. So they're not something that you're going to want to look at. The good examples here is if you're ever in a parking garage, and I'll pick on Target again because it happens to be very obvious and a lot of people have been there. When you go downstairs in the Walnut Creek Target parking garage, if you look up, right, you will see this spray-applied fire-resistant material, right? It's covering up all the steel beams. It's really, really easy to put it on, right? Because basically what you're doing is you're insulating the material from the fire, and you're doing it after the steel is already in place, right? And you have a gun and you just spray it on, right? So it's really easy to apply. And if you overspray in some sections, it's not the end of the world, right? Because it's not a finished quality thing. You're just trying to make sure it's completely covered, right? So here we are. We're starting to apply it there, right? Obviously, there's not too much of it on yet, right? I guess this is intumescent paint. Sorry, I apologize. Okay. The other option that we have, right, is putting on a finished material, right, that finds a way to make it look good, but still provide some fire-resistive properties, right? And so the thing about something like this is it needs to be in an area where there are low fire requirements, right? So if we were in a building that, say, was a hospital, right, we'd be far more concerned with fireproofing than, say, something that was smaller like a grocery store or something, right? Because it's easier for people to get out of a single-story building or a two-story building than somebody that's in a hospital in a bed that needs help to get out, right? So this is going to vary depending on the type of building as to whether this is allowed, right? So the key one that's used today in practice is something that's called intumescent paint. And it's a really cool substance. It goes on just like normal paint, right? It's a little bit thicker than normal paint. It looks like normal paint. You can color it like normal paint. You can paint over it, right, with a different choice of paint. But what it does is when it's exposed to fire, it expands and kind of foams up, right, and provides a fire-resistant piece. And I used to have a video, and I have no idea if I can get internet here, so we're gonna try, right, which is always risky, especially at DVC, but we're going to try and hope that maybe we can get it, right, which probably isn't the case. I'll tell you what, we'll continue with the lecture. I'll try to load it at the break and see if we can show it there. Yeah. Could not connect, of course. Can't connect. Okay, so we're going to go back. I will see if I can load it over the break. Maybe I can preload it in one of the other rooms and bring it in, or maybe I can load it up on this computer so you can see it. But this is a good example because it shows two pieces of plywood. One is just the regular piece of plywood. The other has been covered in this intumescent paint, and it shows a time lapse of how quickly it's basically a gas jet will go through the plywood and not through the intumescent paint. It's a really good example. So anyway, intumescent paint is really great for fireproofing the buildings. So we have a slide like this. This is classic out of the book that shows us cross sections of steel columns, right? That this is how we're trying to cover them up. The top one is covered in concrete, right, on the corners. Notice that it does have the little chamfered corners on it to allow the formwork to come off. This is the spray applied fire-resistant material, that foam stuff, right? It's not really foam. It's more nasty particles would be the best way to describe it. In this particular example, we have our multiple layers of sheetrock that are covering it. And I think this is the lath and plaster piece. It's kind of the antiquated one of the bunch. So what about if we need to find a way to span longer distances, right? The regular traditional steel just isn't cutting it. We need a bigger open space. We need to be able to span that. How do we do it, right? The first way of doing it is to make something that's called a castellated beam, right? And what we're going to do is we're going to take a standard I-beam or wide flange, right? And we're going to cut it in a zigzag pattern, right? And I'll show you it's going to end up looking like that, right? So we're going to cut it in a zigzag pattern. We're going to take the two pieces, split them apart, and weld them back together, right? So what it's doing is it's increasing the overall depth of the beam to give us more spanning capability, right? And so if we look at the drawn examples here, up top we have our basic piece, right? We cut it along that dotted line. We lift it up and shift it and then weld it back together to create the deeper beam, right? In this particular example, on the right here, we're adding another piece, welding that piece in to get it even deeper, right? And so this is all about spanning. The deeper the beam, the longer the span, right? And in a way, we're removing a lot of the non-working materials. So just like when we did precast concrete and we did like hollow core slabs and we removed the non-working concrete, same thing's happening in steel. We're removing the non-working steel, in this case, and giving ourselves a longer span for the same weight, right? So if you were making something like this, ideally you'd use it with some kind of a laser or a plasma cutter or a water jet cutter, right, to be able to cut these pieces out. And so we see here, in this particular case, they're cutting circles, right? It depends. The zigzag would have no wasted material, so maybe they're trying to be more economical so they can collect those pieces and recycle them. But anyway, you get the idea, right? This is ultimately going to be shifted and welded there to make the overall beam. So that's called a castellated beam, okay? If we need even deeper than a castellated beam, we can make what's called a plate girder. And a plate girder is basically a giant I-beam, right, that's made by assembling individual plates of steel, right, and welding those plates together. So you think about when you're driving on the road and PG&E or East Bay Mud dug up the road and they didn't finish in time and they had to go home, and they cover them up with those big steel thick plates, right? Same concept here. We're taking those plates, we're welding them together, and we're making these giant beams out of it, right? And so you can see the size of the person and see the size of the beam, right? So this is designed for really long spanning elements, all right? Because we're majorly increasing that depth. Something like this, something like that, right? Significantly deeper, significantly longer span, or in this case, my guess is this is for some kind of a railroad or something, significant weight. That would be the other thing. Okay? The other thing that we can make is called a rigid steel frame, right? And this is produced by welding the wide flange elements together, right? Or plate girders together, right? And they're set up in a shape, right, that is self-supporting in a way, okay? They're set up in a row for a rectangular building or an array for a circular building, right? And they act a lot like an arch, right? Because they're all welded together, they come down and they rest, and the idea is that any weight that's applied on one of these shapes, right, from the top is going to work its way down through the welded joints. So it's basically like a curved beam, so to speak, right? And it's going to allow all of that right? Long span that comes down into the side. Okay? This, however, if we put too much pressure here, it can cause the whole thing to want to kick out from either side. So it does have outward thrust that a lot of times you have to handle in the foundation itself, right? So this is what I'm saying about they need tie rods, right, or buttresses at the base to make sure that it resists that lateral loading, right? So this is the diagram of it with the splits in it that kind of shows how this is put together. They actually tend to be bolted together in sections, right? They get the span. They're bolted at this nice 45 degree at the corner, right? And they continue down. Usually they taper on the sides down to a base. That's a really puny base, right? Usually they're much more substantial. So there is a fantastic example of this type of building that's around here. Anybody recognize it or been to it? Probably not. Maybe. The construction people maybe have, and they haven't paid attention to it. So the transfer waste station out in Martinez, right? If you've ever been there, it's kind of bizarre. It would be considered the dump in this area, even though basically you dump your stuff and they haul it somewhere else, right? It's a giant, giant building. I mean, like massive building, right? Type of building that you can have full-size, tractors and bulldozers driving around inside, right, without a problem. It's really big, right? It's this exact type of framing. And I've always been tempted to get there and take my camera out and start taking pictures, but it's a little creepy, right? You're in the dump, like taking pictures. But it's a really good example of this, and it's close by, and a lot of you at some point in your lives will end up going there, right, to get rid of a couch or whatever, right? And it's built exactly like this, using one of these rigid steel frames, right, so that you can have a really open, expansive interior without too much framing, right? And so in this particular case, it needs to support the roof, but that's it, right? There's not much more than just the roof. So it's a good example of something like that. We can see examples of it here. In this case, right, you could tell how long of a span this is. It does have a center column, which kind of defeats the purpose a little bit, but you can also tell that you're driving vehicles around inside this building, so you get a sense for the overall scale of this particular building. So if we want to improve our spans even further, right, so we went from castellated beam, we went to plate girder, right, we went to rigid frame, right, now we're moving even further, and we're getting into a steel truss, right, and a steel truss is a triangulated arrangement of steel members, right, that are designed specifically to eliminate the non-working steel, right, and allow these elements to span much further distances than you could, because they're much lighter, right, with a traditional beam, right, spanning much longer distances is what I said. Okay, so the standard piece that we probably are more likely to see looks like a traditional truss, something like this. It's made up of a lot of light, thin elements, right? In this case, it's a light gauge steel truss. And somewhere in the back, there's a little bit of an example of one. So I'm just going to grab this piece. Right? This is like a small mock-up of a light gauge steel truss. It's not actually a piece of a light gauge steel truss. It's something that somebody made. But the concept is the same. It's a lot of lighter, smaller, thinner elements, right, that in their configuration, right, are allowing a much longer distance to be spanned. Right? And so these can take the small scale form, or they can take the really dramatic large scale form, right? And so this is, again, a steel truss, right? The Bay Bridge, the old span of the Bay Bridge, is a great example of a steel truss, right? The old span. Well, yes and no. It's a great example because it is a truss, not because it's really great, right? So this is an example of a truss. The key on a truss is making sure that the elements are triangulated. I'm going to draw for just a second about a truss just to hope to illustrate this a little bit better, certainly because you're going to be making trusses anyway, right? So the idea behind a truss is that we're taking something that would be typically a beam. So let's pretend for just a second that this was a beam, right? You can imagine this as an I-beam, okay? What we're doing is we're taking the web out, and we're leaving what's called the top chord and the bottom chord in their same configuration, right? So we could say that this is a top chord, and this is a bottom chord. Okay? So we want those to stay consistent. Okay? What we're doing, instead of having a solid piece of steel in here, is we're trying to substitute in elements that would keep the top chord and the bottom chord separate from one another. So for example, let's say I put, right, a couple of pieces in like this. Okay? They're serving to keep the top and the bottom chords separate. right? So theoretically, they're working, right, because they're keeping the two chords separate. The problem is, if you put any kind of a lateral load on this, right, we can all see that this would very easily collapse. Make sense? Intuitively? Yeah? So this is something that if you're in a structures class or a statics class, you would have to calculate what all these forces are inside the truss and whatever. I'm never going to ask you to do that, right? But I want you to understand the conceptual, right? If, however, right, I put a diagonal in here, and I put a diagonal in here, right, and I were to apply the same force, right, these diagonals support that force. Likewise, I still have the support vertically. Does that make sense? Right? And it turns out that I actually don't need these pieces necessarily. All I need are the diagonals, right? Because this is forming a triangle, which is a solid shape, right? I can put weight on top of this, and it's going to transfer. Let's say I put weight here. It's going to transfer down in this particular chord. Does that make sense? To the bottom. Okay? However, if I have a point load that's really, really heavy in the middle of something like this, I may end up putting this particular piece back. Right? So there's a bit to truss design, but the idea is that you're taking your particular piece of span, right, whatever it is, and you're dividing it up into triangles. Right? And how you divide it up into triangles can vary greatly based on aesthetic qualities, right, or structural properties, where you need really heavy pieces versus lighter pieces. Yes, sir? It depends a bit on the steel that goes to make up this, right? Typically, and this is one of those, there's always these trade-offs. For its weight, this is significantly stronger, right? But that's not to say that if we had two that were exactly the same depth, the plate girder wouldn't be stronger. Does that make sense? But it weighs significantly more. Right. So it's a bit of a misnomer. The reason that I'm trying to call it non-working steel is to tie it together with the idea of concrete when we remove the non-working concrete. In a plate girder, it's a little bit more complicated. I'm glad you brought it up because at least we can talk through it. The plate is acting with an infinite number of these diagonals, right? Likewise, an infinite number of the diagonals in the opposite direction. So by its nature, it's stronger from a weight standpoint for what it can hold, right? The problem is it itself weighs so much more that you need more structure to support it. So it ends up being less practical, and it's certainly used in some cases, but it's less practical than, say, a truss, right? And so if we're getting up to a large scale like this, right, this is not something that you want to do with plate girders. It's just too big, right? So we're eliminating, so theoretically, right, along the same line, if this was a solid sheet of steel, it would be stronger. But it would also be ridiculously expensive. So we're trying to remove, right, in the balance of cost, right, so that we can get away with a lesser number of elements that cost less, that we can get the same spanning capabilities. And the weight would definitely affect how much in the foundation. So it's a bit of a give and take. I apologize if I overstepped slightly by saying it was non-working steel because, yes, technically it's still working. I'm just trying to simplify the concepts. Okay? So if we move forward from there, right, we can have something that's called a space frame, right? And what that is it's taking the simple concept of a truss, which is normally flat, and changing it so that it's in 2 dimensions or 3 dimensions, right? It's actually spanning one direction and the other direction at the same time, right? It's kind of like switching to a waffle slab, right, from a one-way joist system, right? We're spanning in both directions at once. So what can we do about it, right? We can have very, very lightweight little elements, right? And these little elements can span very long distances, right, in both directions because they're all working together as a network, right? Furthermore, we can push the envelope for what they can do, and we can start to transform the shapes. So this is inside a space frame. It has cladding on one side here, cladding on the outside there, right? This is the section that's providing the primary structure for this particular roof/wall, right? And all of these little tubes. See, there's a density to them. There's a lot of them, right? It's not really a usable space. It's not like you could have a bathroom in here or something. It's not a usable thing because of all the struts, right, that are supporting each of these pieces, all the diagonals working together. But at the same time, it's providing a really nice skin for the building and a support system for the building. So we can end up, from an architectural standpoint, getting something that looks more like this. Right? We have flexibility in what shapes we can make. So if you're trying to design something, architects out there, that has this kind of a curving shape, generally a space truss is one of the best ways of getting that kind of a shape. Right? So this is an example of a space truss that's working together. It has a few special elements, like this particular piece is not part of the space truss system, but it's an additional support for this particular truss system. But you get the idea of this particular shape, right? Not something that would be easily built using any other method of construction, right? Which is kind of the direction of going with the space frame in the first case. Okay, so we're going to take our break now. If you guys would come back at, let's say, 8:05, we'll continue on, right? If you haven't picked up your midterms yet, you can have them now. I will make copies of Project 2, and I'll see if I can get that video to load in the process.